Now, you can't talk about nuclear chemistry or nuclear processes without talking about nuclear fusion. And as a chemist, I really just geek out really hardcore over nuclear fusion, because fusion is fusing together two smaller nuclei into a larger nucleus. So I have just two nuclei here, but it's really smaller nuclei or even particles of the nucleus that we're smashing together and making a larger nucleus. And the reason that chemists geek out so much about this is because the entirety of the periodic table, every element that we know and the newly discovered elements that we're synthesizing in the lab happen because of this process, right? Nuclear fusion is the thing that happens in the core of stars, and when the universe and when the cosmos were created and exploded outwards, then as things started to heat up and fuse together and collide together, then we got these particles that had more and more mass to them. So the elements that we know on the periodic table come from nuclear fusion. Now, we here on Earth use nuclear fission to power things. So we have fission power plants, because that is a process that we've been able to control. But fusion is still something that just requires a little bit too much energy to do on any sort of large scale. We can do it in places like particle colliders, where we're smashing things together at incredibly high velocities in these crazy intense conditions. But even still, we're doing it at a very teeny tiny scale. Okay, so let's talk a little bit about fusion, because it's just so dang cool. All right. So let's think about this process. So we have these two smaller nuclei that we're smashing together and making a larger one. I sort of like my drawing here because it looks like I'm just kind of like putting them together and tink, and then now they're a larger nucleus. But that's definitely not the case. You need really intense conditions, really high pressures, really high temperatures, really high velocities that we're accelerating these things in order to smash them together. And then we get this larger nucleus. And when that happens, then there's some energy that's released. Energy that comes out, and that energy is sort of interesting and large, right? That's a large amount of energy, even for small particles that we're smashing together. So let's do a little thought exercise here. If I have two of the same particle that I'm smashing together, so let's say that the mass of my particle 1 here is m, and I have an identical particle that I'm sticking together with this one. So I smash together two particles with masses m, and then I would expect then that the mass of my resulting particle to be 2m, right? So I'm adding together the two masses. I should end up with a mass of 2m. But it turns out that when you measure the mass of that resulting nucleus, it's less. But it's less massive. And why is that? And well, the why is right here in the energy, right? The energy was lost, and there's this relationship then between mass and energy. And there's a very famous scientist, perhaps you've heard of him. His name is Albert Einstein. And he came up with this relationship of E equals mc squared, where the energy in a process is equal to the mass times the speed of light, which is a constant, squared. Okay, and the speed of light is, if I'm rounding, kind of my 3.0 times 10 to the 8th meters per second. Okay, so this is kind of an interesting process then, because I'm saying that matter can become energy, which is kind of weird, because that just goes against everything. As a chemist, I love Antoine Lavoisier. He's kind of the father of chemistry. And he was the one who really helped to solidify the law of conservation of mass, that whatever it is I start with mass-wise should be whatever I end up with mass-wise. And so this goes against everything that I know as a chemist, and I sort of like it for that reason, right? So we add together these masses. We're expecting it to be 2m. We're losing some of it as energy. So there's this interconnectedness by a constant between these two quantities. And so what we can do then is we could measure that. If we know how my mass changes going from start to finish, then I can find out how the energy changes, which is just kind of an interesting feature, I think. So, you know, as a scientist, we're really less interested in sort of the state of affairs right this second. I'm interested in how it changes. So we can rewrite this as the change in energy is equal to the change in the mass times the speed of light squared. So this is kind of the more interesting, from kind of a problem solving standpoint, feature, because if I can see how the change in my mass happens, or what the change in my mass is, then if I multiply that by the speed of light squared, then that tells me how much energy I'm going to get out of the process, which is just kind of interesting. So let's look at an example, shall we? Let's. Okay. So this is asking us to calculate the energy change in joules per mole for this particular reaction. So I have some pretty small nuclei here. This is my hydrogen. So hydrogen is normally 1 proton, 1 electron. When it has a neutron in it, then we call this heavy hydrogen. This is actually deuterium, named because there are 2 particles of the nucleus, 1 proton, 1 neutron, which it doesn't usually have the 1 neutron, so that makes it slightly unstable and therefore radioactive. And then here's a helium nucleus. So this is helium-3. So normally helium has 2 and 2 when it comes to the protons and the neutrons. So this one's slightly on the light side. So again, slightly unstable. And then when we smash these guys together, I end up with a helium nucleus that's an alpha particle, right? So 2 protons, 2 neutrons, and then a proton flies off in the process. So we smash these guys together, we get to something that's more stable. We lose some particles in the meantime. Okay, so I can look then at the change in the mass. The change in mass for a reaction like this is going to be the mass of the products minus the mass of the reactants. And if you look these up, based on the number of particles that are there, you can look up the actual masses out to very precise numbers in atomic mass units. And there's tables that are available. If you're taking a chemistry class, then you'll probably have a textbook that has a table in it that you can look up these values in atomic mass units, or AMU or U, and you can find the difference then in these guys. So for this particular reaction, my change in mass is going to be equal to, here's my mass of my products. So here's my helium and my proton, again out to a high degree of precision, just to kind of show. So these are in atomic mass units, AMU, or just kind of the international unit, the U. And then I'm going to subtract from that, here's the mass of my heavy hydrogen, plus the mass of my helium, and U or AMU. Okay, so this will give me a delta M. So when you throw that together, your delta M is equal to negative 0.960 atomic mass units. All right, so the negative sign here in the delta M means that I'm losing mass, right? My mass is getting smaller, and it's changing by this amount. If we convert this to kilograms, then this gives us a couple useful things. First of all, if I'm converting to kilograms, what I'm actually converting to is kilograms per mole, right? And that gives me the per mole part for joules. And we know that a joule is equal to a kilogram meter squared per second squared. So I need to have kilograms for my mass here. So I need to convert my atomic mass units. So 1 atomic mass unit, and we know this from just kind of the introduction to the periodic table, is equal to 1 gram per mole, right? So there's that relationship between our atomic masses on the periodic table, that they're both the mass in atomic mass units and the mass in grams of 1 mole of that particular substance. And so that's going to be equal to, you know, 10 to the negative 3rd kilograms per mole. And so we can use that as a conversion factor to convert this to kilograms, and that will be useful. So we'll have kilograms per mole there. We already know our constant. The constant C is our 3.0 times 10 to the 8th meters per second. And so when we plug this into our equation here, here's our delta E, is equal to the change in mass. So I'm converting to kilograms, so it ended up being this 60. I'm changing it to scientific notation just so that I don't have to write out all those zeros. Kilograms per mole. And then my speed of light, meters per second squared. So my delta M times my C squared. Then when I plug and chug through this, then I end up with my delta E is equal to negative 1.762 times 10 to the 12th. And then again, I get, kilograms, meters squared per second squared mole, which is really, a joule per mole. Kind of handy, right? Kilogram meter squared per second squared is a joule, and then the per mole stays the same. All right, so why do I care? I care because that's a big number, right? And so that's the number of joules that I get from 1 mole of this process here. It's 1 to 1 to 1 to 1. So if I have 1 mole here, then this is the potential amount of energy that I could get from 1 mole of each of these that I'm smashing together. That's not a large amount of stuff, right? If I'm thinking about 1 mole of each of these, then it's essentially 2 grams and 3 grams. So we're talking 5 grams worth of material. So this teeny tiny amount of material produces this many joules per mole. What does this negative sign mean? Well, the negative sign means for energy quantities that the energy is being released from the system into the surroundings. So negative energy means that we're releasing energy. So energy is coming out. Which makes sense because my mass change was negative. So my mass is going down. So what's happening? Well, the energy is coming out. Now, I think that numbers like this, well, it's big, but what does it actually mean and what does it actually tell us? Well, I just, did some back of the envelope calculation because, that's what we do as scientists. And I found out that it takes for 1 month to heat an average kind of house size. It takes 7.5 times 10 to the 9th joules of energy to heat a house. So I thought, well, wouldn't it be interesting if I was to see then, how much of this, how many months I could heat my house. So let's find out. Let's just kind of run the numbers because we're scientists. So if I have this much energy that's released, and now, energy is never a negative quantity. I can't have a negative energy. It's just telling you what's happening to it in the system. Is it being released or is it coming into the system? So if I have this many joules per my 1 mole, and then it takes this many joules to power my house for 1 month, then that gives me 2.3493 repeating forever times 10 to the 2nd months. And so that was actually a bigger number than I was expecting because now we're talking, 235-ish months. So let's look at that in years then, because it didn't even occur to me that I'd have to go that far. So let's take 235 months. It's 12 months in a year. Last I checked. That's 1.96 years. So that, to me, gives you a little bit better perspective, or at least that gives me a little bit better perspective. Because if I go back and I think about this reaction, and I say, okay, I have 5 grams worth of material that I'm smashing together, and the energy that's released from those 5 grams could power my house for almost 2 years, that's impressive. You can see why fusion is so such an elusive and interesting concept, right? Because if we think about such a small reaction and such a large amount of energy, you could just really see the potential of that.